the topic for the synchronous machines continue. And here we have the example that a three-phase 5 MVA 11 kV 60 Hertz synchronous machine. It has a synchronous reactance. Excess is 10 ohms, and it has a negligible stator resistance. That means RA is 0. The machine is connected to 11 kV 60 Hz bus and is operated as a synchronous condenser. So you should know what is a synchronous condenser. Condenser is actually another name for a capacitor, and it is used in the industry. We have the control, as we know that we can control the reactive power of a synchronous machine by its excitation. And by excitation I mean that if this is the stator part, this is the rotor of the motor. Rotor is producing the field, and if we control the field current IF, the flux in the stator is controlled, and the voltage that is being internally generated is controlled, and the power angle is also controlled by doing this control mechanism. And our motor, which is connected to a normal supply, in this case 11 kV, it is like just floating, or it is turning freely, but it is also providing Q to the system or absorbing Q from the system. This is the control that we can achieve by IF. So for the first case, it says that neglect rotational losses. It means that there is a bus, there is an 11 kV bus in the industry. For example, this is a three-phase bus. This is our motor. It is rotating. It is connected with the bus, and it is rotating, and it is absorbing no P, no real power. Because for rotational losses, the motor will be needing real power. But if we have no rotational losses, no real power is being assumed. The second thing is, what about the reactive power? That we will decide. Either the motor will be providing, either this synchronous condenser will be absorbing Q, that means it will be taking Q from the grid, or it will be supplying Q, that is the reactive power Q, to the grid. So this is the scenario how it is usually used in the industry. Now let's try to consider this case for the part A. And for the part A, let's see. For normal excitation, by normal excitation it means find the stator current, draw the phasor diagram. So for the normal excitation is actually considered to be when the cos theta is 1. That means the angle between terminal voltage Vt and the armature current Ia is, the angle is 0 degrees. This is the normal. Find the stator current, draw the phasor diagram. Now the stator current is actually the line current. This part is actually the stator current. This means that this is the current that is going out from the stator. So how can we do that? This can be done. So this is also a Y connected machine, and let's try to make its per phase equivalent. And this is Vt, and this is XS. Now as no real power is being transferred between both of them, no real power is being transferred, which means that P equals to 3 Vt Ia sine of angle over XSS. This power is 0. So this automatically means that there will be no current, 0 ampere. There will be no current being transferred. So there is no current that is flowing into or out of the machine, and this makes it that the EA and VT both are equal. EA equals to VT. Now, what is Vt? Vt is actually, as this is a Y connected motor, Vt is equal to V line to line divided by under root 3. Let's see, they have given us line to line voltage, or yes, they have given us line to line voltage, that is 11 kV bus bar. They have so 11 kV divided by under root 3. So our Vt is equals to 6.35 kilovolts per phase, and thus Ea equals to Vt equals to 6.35 kilovolts, and as both are equal. So this is the answer for the first question. Find the stator current. The stator current was 0, and draw the phasor diagram. So if you want to draw the phasor diagram, the phasor diagram for this uh, case will become, this is our Vt with angle 0, and current Ia, which is also 0, and Ea is same as Vt with angle 0 degrees. So this will be the phasor diagram for this case. So the next part, it states that if excitation is increased to 150, so this means that If is increased to 150%. That is the flux in the machine of the normal excitation. Find the stator current and power factor. What will now be the stator current and what will be the power factor? Draw the phasor diagrams. Okay, so for the part B, we know that Ea equals to K phi omega. So if this is increased 150%, this will also increase 150%. For so in the above circuit, Ia is actually equals to Vt 0 degree minus Ef 0 degrees, because both are in same phase, and this is Jx of s. Both are in the same phase. That means no real power is being transferred between them. And here synchronous reactance, we have 10 ohms. So this will actually become 6351 minus 1.5 times. So this will, we will multiply this voltage by 1.5 times, because 150% increase, 6351 divided by, this is angle is 0, this angle is also 0, 10 angle 90 degrees. So what will happen is, the value of the current will now become 317.55 with an angle of 90 degrees. And so the power factor will be cos 90, that is equals to 0, and as the angle is positive, it will be a leading power factor. Now if you want to draw this diagram, we can draw this diagram by, so let's draw it here. So here was Vt, and here we have Et, we have Ia excess, sorry, the voltage, here we have Vt, and the value of Ef has increased. Ea, sorry, I write it Ef, this is actually Ea. The value of Ea has increased. This will be like this. Ea, this is actually IaJXS, and actually this is the current Ia. So when we multiply this, it becomes, and this vector from here up to here is E of A. So this is how. Now there can be one question there that can cause confusion also, that why is a current flowing when real power is 0? So what I have said, that the real power is 0. It is actually the real power is 0. It can be 0 when sine of this angle value. So this is actually happening because it is on we are using the normal excitation where EA and VT both are equal. But for the part B, what we have done is we have increased the internal excitation of the machine, and that is why now a current is flowing. Current is flowing but with a 90-degree phase shift from V of t. So what we have done is we have increased EA 150 times. So now this is at larger potential than Vt. So there is a flow of current, but that current is at an angle of 90 degrees. That means still no real power is being transferred. Because we know that for real power we have formula Vi cos of theta. So still there is no real power being transferred, but there is a reactive power being generated by the machine. The third part is similar, in which it says that if now excitation, that is the field current IF, is decreased to 50%, find the stator current and power factor. So it is similar as that, but what will happen in this scenario is that in for the part C, let's see, for the part C, IA will become Vt minus EA over XS, and what will happen in this scenario is Vt is 6351 minus 0.5, that is decreased as 50%. First it was increased 6351, and this will be similar 90 degrees, similar to what we have done here, but for the new scenario this will be like this. Again the angle is 0 here, and here the angle is also 0, and so the power factor will become, so the value of IA will be 317.55 amperes. But now the current is lagging, but how much lagging? Exactly 90 degrees. So again there is no real power transfer, and the power factor again is 0, and but it is lagging. This means now the motor is absorbing Q. When it was leading, it was when the motor was generating Q. The next question is about the next part is when it considers that the motor is acting as a condenser, but it is also there are rotational losses in the motor. That means it is also absorbing P, the real power. So rotational losses are 80 kilowatts. Find the stator current and excitation voltage for normal excitation. Now again, for the normal excitation, what it means by normal excitation means when both the current and voltage are in phase, that is unity power factor. So for the normal excitation, we have cos theta equals to 1, or the angle between Vt and Ia is 0 degrees. So here it has given us the power that the motor is absorbing, that is equals to 3 Vt Ia cos of theta, and that is actually equals to 80 kilowatts, that means 80,000 watts. So we can calculate Ia, and this is actually 1. So Ia will become 4.2 amperes with angle 0 degrees. Now this is the current that is being absorbed. So we can calculate EA, the value of EA. So the value of EA is equals to Vt minus IA J X of S. VT we know is 6351 with an angle 0 degrees, minus IA is 4.2 amperes angle 0 degrees, and X of S is 10 angle 90 degrees. And when we solve this, the value of EA will be 6351 with an angle of 0.4 degrees. This is 651 volts, and the phase voltage 65 volts. And to draw the phasor, we can see that this is VT and there is a current 4.2 ampere here. The current is the current is also in phase with VT, and there is a value of EF, and there is a power angle that is 0.4, and there is this EF, this is 0.4. So this is how we can solve this question. I hope it helps. Thank you.